Hello everyone. Welcome to the Machine Learning Teach by Doing project, day 6. In the previous 5 days, we have covered a number of things, including the types of ML models, installing Python and running your first ML code, the 6 steps of doing any ML project, etc. So, if you have not seen those previous lectures, please go through them and then you can come back to this lecture. Today is a very interesting topic. Today we are going to develop our first machine learning algorithm. It will be a lecture on linear classifiers. I have planned two lectures on this. One will be today and one will be tomorrow. So today will be the part one of this lecture. I'll also be writing many things in front of all of you today. So please make sure to have a pen or a paper ready. That will tremendously improve your understanding. So let's get started, everyone. Before we get started, I would like to share that for today's lecture, I have made 4 pages of handwritten notes, which I'll be sharing with all of you. And this presentation PDF also I'll be sharing, which will be found in the information section of the video. So all that material will be available to you. So let's get started with today's interesting lecture where we will develop our first machine learning algorithm, which is linear classifier. The problem which we will be taking for this is the cats and dogs classification. Remember in a previous lecture we looked at the teachable machine interface where we performed an image classification between two types of categories. We gave the category 1 as cats, we gave the category 2 as dogs, and then we uploaded several pictures. We uploaded 10 images of cats, we uploaded 10 images of dogs, and then we ultimately run the AI model. Today we will be developing our own AI model which will be able to classify between cats and dogs. So we will dive a bit into theory as well as practical. One more thing I would like to share with all of you is that if you go to the Microsoft scores and if you look at classification, the way they do classification is directly using Python and directly from projects. But there is no mention of the theory of classification or the mathematics behind classification. Whereas in today's lecture, we'll be following MIT's course where they dive a lot into the theory and the mathematical understanding behind linear classification. One of the goals of this series is not just to do practical projects but also to introduce you to the foundations of machine learning. We will, of course, do practical classification problems as well, but initially, all of you guys really need to understand the theory. So, this initial first lecture and also maybe tomorrow's lecture will be geared towards theory of classification, and then we will take hands on examples where we will demonstrate projects in Python. So, the problem which we are facing is that we have to identify between cats and dogs. And there is one more thing, we have measured two properties based on all of these images. We have measured the whisker length and we have measured the ear flappiness index. So we know that dogs have flappy ears. So we have constructed a metric called ear flappiness index. And we know that cats have longer whiskers. So we have measured another thing called whisker length. Now, your task is that based on these two measurements, you have to build a linear classifier so that if I give you any other new animal, you take these two measurements again. You take the ear flappiness index, and if you measure the whisker length, your model should be able to predict whether it's a cat or whether it's a dog. I hope everyone has understood this problem. Imagine you have 10 cats and 10 dogs, and you have measured the ear flappiness index and whisker length of all these animals. That's your training data. The problem is to construct a linear classifier model which can classify any new animal. So let's say now I give you another new animal and you measure its flappiness index and the whisker length. Based on the training data, your job is to classify the new animal and take into input the measurements, the two measurements, and then classify whether it's a cat or whether it's a dog. Great. I hope everyone has understood this problem. Now, whenever anyone gives you any machine learning project like this, your first instinct should be to go back to the 6 steps of any machine learning project. I think it was day 3 of this series where we looked at the 6 steps of any ML project, and we saw that the 6 steps are gathering the data, generating hypothesis class, defining the loss function, fourth is finding the algorithm, fifth is running the algorithm, and sixth is validating the result. In today's lecture, we'll be looking at especially the steps number 1 and steps number 2, and a bit about step number 3. In tomorrow's lecture, we will look at step 4, step 5, and step 6. So, okay, you have been given this project and you have these 6 steps of any ML project. So, let's start with the first step. Let's start with gathering the data. So, now I am going to this whiteboard where I'll be writing in front of you. So, our task right now is to generate linear classifier or to find the best possible algorithm. And as I mentioned, we looked at the step 1. Step 1 is gather the data. Gather the data. Now let's look at the data. I'm going to plot the data here. The data looks something like this. This is the y-axis and this is the x-axis. The x-axis label is whisker length. Whisker length. And the y-axis label is ear flappiness index. Okay, and so the first data point will be for dogs. So dogs generally have flappy ears and shorter whisker length. So all of the data lies here. This is the data which we have collected. This is for dogs. And for cats, all of the data lies here. So cats generally have a shorter ear flappiness index and their whisker length is usually larger. So this is the data for cats which lies here. Now our aim, let me switch back to the blue. Our aim is to find, when I say find the best linear classifier, our aim is to find the best straight line which separates the above data. Which separates above data. So that's our aim. And the further aim is that whenever someone gives us a new data point, let's say someone has given us a new data point, uh, which is somewhere here. Let's say this is our new data point. Based on that straight line, we should be able to classify whether it's a cat or whether it's a dog. So this is the aim. So if we go to step number 2, we have to generate a hypothesis class. And since we are building a linear classifier, the hypothesis class will be all the space of straight lines which are possible. So let me draw the above graph again. So uh, let me draw the dog data. So this is the dog data and this is the cat data. Okay, now the hypothesis class is all possible straight lines which can exist. So let's see. So the hypothesis class can visually look something like this. Let me use orange color for this. So the hypothesis, it can be this line, 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 it can be this, it can even be this. There are basically infinite number of straight lines which are possible, which can be drawn here, right? So this is basically our hypothesis class. The question is this: out of all these possible straight lines, how to find the best one which separates the above data? How do you even start thinking about what do you mean by the best straight line? There can be infinite possible straight lines, right, which classifies the data, and intuitively we know that this line generally is good, it's a good separator, but maybe this is not a good separator. Intuitively we know this, but how can we mathematically get to the best hypothesis? So this is my step number 2. Step number 2 is generating the hypothesis class. Okay. Now, the hypothesis class, currently we have just visualized it, right? It looks like a straight line. Now, let us look at the mathematical representation of this hypothesis class. How to mathematically represent this hypothesis class. So remember that step 2 is not yet over, because in step 2 we have to mathematically represent the hypothesis class. It's not enough to just visually see that okay, my hypothesis class is all the bunch of straight lines. What does it mathematically mean? So all of us know that the equation of a straight line is ax plus by plus c equal to 0, right? So the mathematical representation is going to look something very similar to this. So here is how the mathematical representation is going to look like. Let's say one more thing which I want to mention is that in classification problems, the answer is either plus 1 or minus 1. So for dogs, our answer is going to be plus 1, and for cats, our answer is going to be minus 1. So all the dog data I am going to represent with plus signs here. This is the dog data, and all the cat data I am going to represent with minus signs here. So let's say the hypothesis class is something like this straight line, or one possible hypothesis is this straight line. So the mathematical representation of this straight line is going to be theta 1 x1 plus theta 2 x2 plus theta naught equal to 0, where x1 is my x coordinate and uh, x2 is my y coordinate. What is x1? X1 is basically the whisker length, and x2 is basically the ear flappiness index. So this is my hypothesis class. The second question, and all of you must be knowing this equation because this is just the equation of a straight line. There are three variables here: theta 1, theta 2, and theta naught. As I vary all these variables, I get a huge bunch of straight lines in this two-dimensional space. Now there is one more thing which we need to consider. This is the hypothesis class, that's correct, but let's say if I give you a new input, let's say if I give you a whisker length and the ear flappiness index, how are you going to tell what's the output? So the hypothesis class, basically this is the hypothesis, right? Let's say my hypothesis is this: if the hypothesis receives an input x1 comma x2, the output should be whether it's plus 1 or minus 1, whether it's a dog or whether it's a cat. That should be the output, right? So we need to somehow convert this kind of a linear representation to a function, so that when this function takes an input, it should give an output. And one of the key factors for constructing the function is this normal function, basically this normal line which is perpendicular to the straight line. Essentially what we are going to say is that if the point is to this side of the normal, then I'm going to say the answer is plus 1. If the point is on this other side of the normal, then I'm going to say the answer is negative. The way to express this mathematically is using a function called as sine. So sine is just the positive or negative sign. So sine of basically theta 1 x1 plus theta 2 x2 plus theta naught. What this sine function does is that, so this function will be equal to plus 1 if theta 1 x1 plus theta 2 x2 plus theta naught is greater than 0, which means if it's on this side of the normal. And this function will be equal to minus 1 if theta 1 x1 plus theta 2 x2 plus theta naught is less than 0. So now we have a function, right? Now basically one way to look at the hypothesis class is sine of theta 1 x1 plus theta 2 x2 plus theta naught. And then whenever you receive an input which is x1 comma x2, we will have an output as plus 1 or minus 1, because the sine function essentially returns only two types of outputs. It returns an output of plus 1, uh, it returns an output of plus 1 if theta 1 x1 plus theta 2 x2 plus theta naught is greater than 0, and it returns an output of minus 1 if theta 1 x1 plus theta 2 x2 plus theta naught is less than 0. So the formal way or the mathematical way to represent the hypothesis class is something like this. So the mathematical way of representing the hypothesis class is h, which is the hypothesis function, x, which is the input, then the free parameters, which are theta 1, theta 2, and theta naught. So this hypothesis function is sine of theta 1 x1 plus theta 2 x2 plus theta naught. And the sine function has already been defined over here. So essentially this is my hypothesis class. This is just a mathematical way of saying that my hypothesis involves all the possible bunch of straight lines in a two-dimensional space, and if the point exists to the this side of the normal, then my hypothesis will say it is plus 1. If the point exists on the other side of the normal, then my hypothesis will say that this is minus 1. Don't worry if you have not understood this. We are going to take a very practical example just right now. So the hypothesis is generated, right? Now the next step is defining the loss function. But before that, I want to explain this to you with a practical example and not just mathematically. But just keep in mind right now that our task in this problem is to find the optimal theta 1, theta 2, and theta naught. That's our task. Because this hypothesis can take infinite values of theta 1, theta 2, and theta naught, right? Among all these possible straight lines which we saw before, how do we find the best possible straight line? And let us also further understand what does this sine function really mean. So let us take a practical example, which I am going to just draw right now. Let us take actual data and let us construct two hypotheses and check how they are doing. So this is my y-axis, this is my x-axis. So on x-axis, I have whisker length, and on the y-axis, I have ear flappiness index. Okay, I'm going to take 4 data points for dog, and I'm going to take 3 data points for the cat. So for the dog, my first data point is, just a minute, I'll use maybe plus 1 plus sign for the dog data points. So my first data point is this, which is 1 comma 1. My second data point is this, which is 1 comma 2. My third data point is this, which is 2 comma 3. And my fourth data point is this point, which is essentially 2 comma 4. So this is my dog data, and my cat data is this. I'll have two data points or three data points in my cat data. So the first cat data is 4 comma 2. The second cat data is 5 comma 1, and the third cat data is 5 comma 3. Okay, now your question is that given these set of data, how do you find the best possible straight line which separates these two, right? So let me generate two hypotheses, or let me take two straight line as example. The first h1, which is the first straight line belonging to our hypothesis class, that has the equation of y minus x plus 1 equal to 0, and the second straight line, which is h2, has the equation that y minus 1.5 is equal to 0. Now let me plot these two straight lines, okay, for visual understanding. So the first straight line h1 actually looks something like this if you really plot it. So this is h1. I am not exactly plotting it, but just for visual demonstration, this is h1, and h2 actually looks something like this. So visually, can you try to understand which is the good classification, which is the good algorithm among h1 and h2? It's clearly h1, right? Because h1 seems to separate the two classes perfectly. H2 does not seem to separate the two classes. For H2, these points appear on one side and all other 5 points appear on the other side. So these two also H2 is classifying as dogs, whether these, but these are actually cats. And this point will be classified as a cat, but it's actually a dog. So H2 is wrong. We know that. H1 is correct, or H1 is, rather than wrong and right, H1 is better than H2. Now let us try to see whether we can come to this conclusion mathematically using our uh, mathematical representation of H, right? So I am going to construct a table here. Uh, so let me write the 7 points. The first point is 1 comma 1, 1 comma 2, 2 comma 3, 2 comma 4. Remember, these are dog points, and 5 comma 1, 4 comma 2, and 5 comma 3. These are cat points. Let me give some separation here so that. Okay, so this is the first cat point, this is the second cat point, and this is the third cat point. So just for the sake of reference, I'm going to. So this is the dog data whose actual answer is +1, and this is the cat data whose actual answer is -1. Now let us actually test the mathematical uh, version of both the hypothesis class. We visually know that h1 is better than h2, but let us see if mathematically we can understand this. Okay, so for h1, the mathematical function is sine of. So let's see it. Sine of theta 1 x1 plus theta 2 x2 plus theta naught, right? So which is sine of y minus x plus 1. So let's do this. So the value for this will be sine of 1 minus 1 plus 1, which is sine of 1. The value for this will be sine of y minus x plus 1, which is sine of 2. This will be sine of 2, and this will be sine of 3, because y is equal to 2, x equal to y equal to 4, x equal to 2. So y minus x plus 1 is 3. Now let us see the sine function. The sine function basically is just if something is greater than 0, the answer, if something is greater than 0, the answer of the sine function is +1. If something is less than 0, the answer of the sine function is -1. So the answer for this would be this greater than 0. So it's +1. This is also greater than 0. 2 is greater than 0, right? So this is also +1. this is plus 1, and this is plus 1, since all of these inputs of the sine function are greater than 0. Now let us see for the cat. So this will be sine of y minus x plus 1, which is sine of minus 3. This will be sine of y minus x plus 1, which is minus 1. And this will be sine of y minus x plus 1, which is sine of minus 1. So all of these inputs are negative. So the output of the sine function will be minus 1. So here you can see this hypothesis class has classified all the dog values correctly as plus 1. See, plus 1, plus 1, plus 1, plus 1. And it has classified all the values of cat as minus 1 correctly. Minus 1, minus 1, minus 1. This is exactly what we predicted here. H1 does a great performance on the training data, because all the dog values are on one side of H1 and all the cat values are on one side of H1. So the mathematical understanding matches our visual understanding. Now let us check for H2. This will be sine of theta 1 x1 plus theta 2 x2 plus theta naught, which is y minus 1.5. So let us check. So this will be sine of y minus 1.5, which is sine of minus 0.5. This will be sine of y minus 1.5, which is sine of zero point 0.5. This will be sine of 1.5, and this will be sine of 2.5. So this will actually be classified as minus 1 now, because the input to the sine function is negative. This will be classified as plus 1, this will be classified as plus 1, and this will be classified as plus 1. Let us see this. 5 comma 1. So y minus 1.5, so it will be sine of minus 0.5, y minus 1.5. So this will be sine of zero point 0.5 and y minus 1.5. So this will be sine of 1.5. So this will be minus 1, this will be plus 1, and this will be plus 1, since the inputs here are positive. So here what we actually see is that this hypothesis class has made mistakes. This has made mistakes because it has incorrectly classified. So it has incorrectly, let me choose the color as pink. It has incorrectly classified this as minus 1. So this is an error. This is a dog value, so its correct answer is plus 1, but it has incorrectly classified it as minus 1. Let's see whether this visually makes sense. So this is the second line, right? So this is H2, and we can see that it is correctly putting these three values, but this value for a dog it's classifying as wrong because it comes on the other side. Similarly, visually we know that, let's see visually how many other mistakes it is making. This is another error, and this is another error for the cats, because the correct answer for cat should be equal to minus 1. So the only correct point it classifies for the cat is 5 comma 1, which is this point. That's correct, right? Because according to this H2, all the things which lie here are cats, and all the things which lie above are dogs. So the only point it correctly classifies is this. These both points it classifies as dogs, so these are wrong. Wrong by H2. So visually we saw that H2 is not probably the best separator, and that is also confirmed by this mathematical operation. So the number of mistakes. So now this gives us an insight into the loss function, right? We are kind of intuitively already using the loss function. So define the loss function. So we are intuitively already defining the loss function as number of mistakes. So step 3 is define the loss function. And the way we will define it as the number of errors made by the hypothesis. Number of errors made by the hypothesis, right? So for H1 and H2, let's compute the loss. So H1 makes 0 mistakes, so the loss is 0, and H2 makes 3 mistakes, so the loss is 3. And remember, the goal in this ML project is to find the hypothesis. So as we mentioned here before, The goal is to find the best straight line which separates the data. And now we understand what we mean by best, right? We need to find the straight line which gives us the lowest possible error. So here we can see that among these two lines, H2 is not good, so we will reject it. And H1 is good. Great. So up till now we have reached step number 3, right, of this ML project. But still we have to find the how do we find the best possible algorithm? So still we have not essentially defined the algorithm, right? We know up till now we learned how to evaluate between two hypotheses H1 and H2. But what about other hypotheses? There might be so many other straight lines, right? There may be so many other straight lines. How do we find the best possible one? We have just evaluated one. There must be so many other straight lines. So in the next lecture, we'll be looking at step 4. Step 4 is basically finding the best possible hypothesis. In this step, we will actually write an ML algorithm. We'll write an algorithm which finds the best hypothesis. We'll write an algorithm which finds the best hypothesis. So this is where ML actually comes into the picture. As a human, how will we find the best possible straight line, right? So we will define the ML algorithm in the next lecture. Meanwhile, if you can think about it and comment in the chat, what can be a possible algorithm which can give us the best possible result? Mathematically, how can we arrive at the best possible result? In this infinite space of linear functions, how do we find an algorithm which the computer can run and arrive at the best possible hypothesis? Think about this in the next lecture. uh, Please be active on the comments, because I've tried to make this particular lecture as interactive as possible, and I'm deliberately writing everything in front of you so that you really understand. So I did not just leave it at this sine function here, because I know that it is a difficult concept to understand. So I deliberately took a practical example below here, and I tried to show how this sine function actually works in practice. This is the approach which we'll be following throughout this series. So in the next lecture, we'll be looking at step number 4, step number 5, and step number 6. One thing to also remember is that this is why I want to focus a bit on theory, because if you directly jump to the applications, right, as which is covered in the Microsoft course, you will not really grasp these fundamentals which we are going through right now. So we will of course come to the theory, but we need to go through these fundamentals as the building block. I have summarized all of my learnings and what I showed you in these lecture notes. These are 4 to 5 pages of lecture notes. It's a bit condensed today, but try to go through these in detail. Try to go through this video and write on your own. Maybe you can take 2 examples on your own, take 2 hypothesis class on your own, and evaluate the loss function like we evaluated here. That way you will also understand exactly how this sign operator works. Okay, that's it for today's lecture. I will see you in tomorrow's lecture, where we will discuss step number 4, finding the algorithm, step number 5, running the algorithm, and step number 6, validating the results. Please stay motivated throughout the course of this series and write along with me. The reason I'm making this ML teach by doing is so that you don't lose motivation. And as you can see, I'm trying to make the lectures as interesting and engaging as possible by writing in front of you. Thank you so much, everyone. I'll see you in tomorrow's lecture.